Tonight, we welcome Larry Bartoszek. Larry has degrees in mechanical engineering and physics from the University of Illinois and is an Illinois licensed professional engineer. Larry is a member of the American Society of Mechanical Engineers, the Chicago Society for Space Studies, and the National... What are you doing? Just pushing you into camera line. Oh, splashing into your camera. There you go, that'll do. Where was I? Larry is a member of the American Society of Mechanical Engineers, the Chicago Society for Space Studies, and the National Space Society. He's also Vice President of the International Space Elevator Consortium. Larry owns Bartoszek Engineering, a consulting firm which specializes in mechanical designs for the nuclear and high energy physics research community worldwide. And his firm has worked for many national laboratories, universities, and governments, and experiments all over the world. Larry started working on the space elevator as a hobby in 2004, developing conceptual designs for climbers as outlined in The Space Elevator by Edwards and Westlings on a concept from NASA studies. He has given many presentations at several space elevator conferences, and in July of 2024, Larry was elected Vice President of the International Space Elevator Consortium. So, ladies and gentlemen, mainly gentlemen here tonight, can you put your hands together and welcome Larry to our meeting?
Okay, so tonight I'll be talking about the space elevator and moving into space. I have additional material that was courtesy of Brad Edwards and material from the Space Elevator Consortium. And so I'm going to cover the basics of how the space elevator works, some ideas of what the space elevator could do in the future. I'll show my climber designs. I'll show critical areas of research, and I'm including some brand new material which hasn't been published yet, but will be published in May, about a study report that we have been working on for the last 2 years on how to power climbers on the space elevator. So the critical areas of research are tether material. That is the thing preventing us from having a space elevator today. High power beaming systems, those are just a matter of scaling up known technology, and higher performance motors. And that is happening. That's actually very exciting for us. So it started as a hobby and has somewhat migrated to be an obsession since 2004. If you want to know really good nuts and bolts information about a space elevator, this book, which is 20 years old, is still well worth reading. So I definitely recommend it. We also have references at the ISEC website, isec.org/studies, where all the study reports from the last 10 or more years are. And in science fiction, there have been a number of stories that have featured a space elevator, starting with Arthur Clarke's Fountain of Paradise. I've read most of these, but not all of these. And there have been a couple of editions in movies and television series, like the Foundation series, for example. So here's the basics. I am the Earth, okay? And there is a rope tied around my belly, which is the equator. And the rope initially would be dangling straight down if I wasn't rotating. But I start spinning around. And what happens? The rope stretches out. There's a rock on the end of the rope. And you can see there's an ant crawling on the rope. That's a climber on the tether. And the rock is 100,000 kilometers up in space as a counterweight. Geosynchronous orbit is only about 36,000 kilometers up from sea level. So you can climb this ladder into space without using rockets. I hope that's pretty intuitive. So gravity falls off really fast as 1/r². And this is a scaled image of the space elevator. So here is the Earth to scale, and here's a 100,000 kilometer long tether with a counterweight at the end. You can see geosynchronous at 36,000. Think this scale is measured from the center of the Earth. but we always think of geo as measured from sea level. But of course, anything associated with gravity is always calculated with respect to the center of the Earth. And the only point on the elevator that is truly in orbit is a point at geo. And so what happens if you let go of the tether below geo? You're not traveling fast enough to be in orbit, so you fall back in a parabolic arc to Earth. If you're high enough, you can go into a very highly elliptical orbit by missing Earth on the way down. If you let go at geo, you don't move, you're in orbit. You just hover next to the tether. If you travel beyond geo, now you are moving too fast to be in orbit around the Earth. And if you let go, you're on your way to somewhere else. And 100,000 kilometer long tether can send you anywhere from Venus to the asteroid belt with no propellant to get enough delta V leaving the Earth. If you want to get there faster, you would let go and then use some propellant. And of course, you have to bring enough propellant to stop when you get there, because the elevator is not going to do you any good when you're at your destination. And think of the term crack the whip, which when I give this to younger audiences doesn't seem to mean anything to them. So let me know if that needs to be explained. Now, why not just use rockets? Rockets carry their fuel with them, and they have to carry enough fuel to boost their fuel. This is what's called the tyranny of the rocket equation. And if you look at the amount of material right up here that got to the moon, it's on the order of 1.5% or less. That's the best you can do with chemical rockets. You use an enormous amount of the initial mass as fuel. The space elevator is going to be powered by an external power source from the ground or from space, so it has no onboard fuel. And it has a way higher payload ratio that is constant at any altitude. The cost for putting things into space during the space shuttle era was $25,000 per kilogram. SpaceX has lowered that by a factor of 10. The cost could go down at least another factor of 10 with a space elevator. So once you have it, what can you do with it? I don't know if you guys talk about space settlement a lot, but the National Space Society that I am a member and a space ambassador for talks a lot about putting 1 million people in space. And a Stanford torus is a very comfortable place to live and work because it has spin gravity. So if you have a space elevator, you can observe near Earth objects from the apex, from the counterweight effectively, and you can stock devices there to change their trajectories if needed. And the point is that we have a very hard time seeing NEOs that are coming from the sun. We don't get to see them until they're very close to us. The further away you can see something that has a trajectory that intersects the Earth, the smaller the object that you need to change its trajectory so that it doesn't collide with the Earth. You could build a space dock in GEO for really massive construction projects, solar power satellites, interplanetary vehicles, asteroid and lunar mining can happen, and you can have processing centers in GEO. One of the early things that I designed the climber payload to be was liquid oxygen. You could build a LOX and fuel depot for interplanetary missions, and then you can launch interplanetary missions from the tether above GEO. So this is just an idea, an artist's rendering of what the inside of a Stanford torus might look like. And I gave a talk a couple of years ago about how difficult it would be to ship live full-grown trees up to the Stanford torus on the space elevator. That was kind of an amusing exercise from my point. But you can see it's big. These things weigh 10 megatons, according to an old study that was done by NASA and Stanford. And it's not reasonable to bring up all that material from Earth. But the elevator would be perfect for bringing up the mining equipment that would get you the lunar and the asteroid resources that would allow you to build such large things in space. So what's the overview of the system? The first elevator, we're talking about 20-ton climbers with 13-ton payload capacity. Actually, these units are TON, but it's really metric tons. So that's what we're talking about. Constructed with existing or near-term technology. The cost estimate that is in the Edwards book that is over 20 years old was $10 billion in 15 years. And it was written in 2003. So it's been 15 years, 2003, 28. Yeah. And we don't have a space elevator. The research on producing the material is going a bit slower than we had hoped. So when you see a dark background slide, that's a slide that I actually got from Brad Edwards. He made a series of public slides that anybody could use. And they embody a number of concepts, basic concepts about the elevator. You can see he's using power beaming to collect light from lasers on the ground to power the climbers. He's using red light. We've learned that red light's not going to work. Infrared is eye safe, but it diverges too quickly. I have the study talks all about that. Green light is the light you want to use if you're going to beam from the surface of the Earth into space. So what kind of materials for the tether? Well, back in 2003, when Edwards wrote the book, he was planning on using carbon nanotubes. Carbon has the strongest covalent bond to itself. And you can get really the strongest material in the world out of carbon allotropes. There are currently 3 candidates. Graphene superlaminate is a 2D sheet material. Carbon nanotubes are still in the running, and hexagonal boron nitride. They're strong enough, but there are manufacturing issues with each one. We don't know how to make them long, and their strength goes down as you make them longer. And the material has many uses on Earth. We use short carbon nanotubes today in electronics for a variety of things. And this is what you can do with graphene. I also have a model of graphene right here, which is 3 layers of carbon atoms where in the plane they are bonded together with covalent bonds. The gray bonds in this model are covalent. The purple bonds in between layers are van der Waals, and van der Waals bonds are much weaker. And one of the things that we discovered in the 2023 study is that even if you layer up thousands of layers of graphene to get the tensile strength that you need, it doesn't have the shear strength that you need to climb it with wheels that are pressed up against the surfaces. We think we know how to create what we're referring to as spot welded joints, which basically convert some of the dual layer or multi-layer graphene into hexagonal diamond. So that little center of diamond would act as a bond between layers to raise the shear strength. And you need to be able to do that to some percentage, like 10% of the area of the tether, to get enough shear strength to climb it with the wheels. This work is all still going on. This is another view of the Canada tether materials. You can make nanotubes out of hexagonal boron nitride, which is boron and nitrogen atoms bonded together, which is roughly as strong as carbon nanotubes, slightly less strong. And as I say, all of these things right now, we're trying to figure out how to make them perfect enough in large quantities so that you can run. Matter of fact, this is what I think we need first. We need something equivalent to a 3D printer or one of Drexler's nanoassemblers that would take graphite powder, pencil lead, anything that has carbon in it, and structure it into these very ordered layered sheets, and then reel it up on a reel. If you build this kind of invention, you will become very wealthy, because this material could be used for sports equipment, military applications, building construction, anything that requires certain electrical properties and the strongest material in the world. Now, back in 2003, Edwards realized that if the elevator is going through low Earth orbit, it's going to be bombarded by junk in low Earth orbit. And 20 years ago, there was less junk than there is now. So he proposed a curved ribbon so that there is no trajectory where a particle in LEO can sever the ribbon by cutting all the way through it. And the idea is if you've got something large enough on collision with the tether that you have to move the tether out of the way. And we can talk about how you do that, but that was the original reason why the base of the tether was intended to be on a floating platform that was powered so that you could move it in the ocean. So this is the Edwards deployment scenario, and it's similar in concept to how you build a bridge across a chasm by first firing a bow and arrow across the chasm, carrying a light rope, a light string, which then you use to pull a heavier string across, and a heavier rope, and a wire rope, and so on, until you have the ability to start building structure. And the idea is you have a spacecraft which is built in low Earth orbit. So you have to bring up the pieces on, he was originally planning on using the space shuttle. Now we can use Falcon X's or Starships or whatever to get into LEO with relatively heavy payloads. You build an MHD rocket, an electric magnetohydrodynamic rocket, which carries the primary spool up to GEO. And once you get to GEO, here's that rocket. The reason Edwards thought it was a good idea to make it an MHD rocket is because you could power it with the lasers you were already building on the ground to power the climbers. So you once the spacecraft, the deployment spacecraft is out past geosynchronous orbit, you begin to unwind the tether, and eventually it gets down to the surface of the Earth where you grab it in a ship. It comes down through the atmosphere, it's got a beacon on it, and a ship grabs it and attaches it to the platform on Earth. And at that point, what Edwards imagined was the heaviest climber that could only go up the pilot ribbon would weigh 900 kilograms. And it would carry a spool of material that it would then attach to the ribbon as it was going up. Now, we've been trying to simulate this process and understand whether or not it actually works when you have a tether which has a stress distribution in it caused by hanging 100,000 kilometers. And it's not completely clear to me anyway that this augmentation scenario of adding strips of ribbon to the tether actually works. One possibility is you attach it at the ground, you unspool it as you go up, but you don't actually attach it to the pilot ribbon until you have another climber go up from the bottom so that both ribbons are at the same stress state. That's one possibility that as a mechanical engineer occurs to me. And then over a period of 2 years, 230 construction climbers would go up, and each time one goes up and adds a length of ribbon, it would augment the mass of the ribbon and its capability to lift climbers by about 1.3%. So at the end of 2 years, you've got a ribbon that can now hold a 20-ton climber. And historically, that's the point where we say we are ready to do commercial business. Once you have a 20-ton climber, you have the ability to lift payloads that are useful. You notice that the construction climbers all pile up near the anchor because every time you make the ribbon heavier, you need to make the counterweight heavier. So that's a convenient aspect of this deployment scenario. We're not sure that this deployment scenario works for graphene for a variety of reasons. To get graphene stacked like this, if you start with monolayer graphene, you have to do it in a vacuum because there can't be any of the adsorbed gas layer that normally adheres to everything in our atmosphere. So it might be better to make multi-layered graphene in GEO, manufacture it in orbit, and then extend it down to Earth and up to the apex. We're still working on that concept. Now, how do you send power to the climber? The study that we just completed shows that we do not have the technology to store enough power on the climber to do the trip, or we don't have the technology to release the energy necessary to drive the motors. So it's got to come from somewhere else. And we have several different designs. We have laser designs, we have microwave designs, we have solar designs. And we started looking at a conductive tether. Can we run power up the tether? We found out recently that even though single layer graphene has the highest electrical conductivity of any material on Earth, once you layer it up with van der Waals bonds to neighboring, once you have as few as 10 layers of graphene next to the monolayer, the electrical conductivity of the assembly goes down by 2 or 3 orders of magnitude. It's very disappointing. Let's just put it that way. So it becomes a semiconductor when you layer it up. It becomes far less conductive than metals at that point. So we are not really thinking that the conductive tether is a serious contender. We do have one electrical engineer who's continuing to look at it to see if there's anything we can do. And one possibility is you put hexagonal boron nitride layers in between mono layers of graphene. And if you have 10 layers of insulator, hexagonal boron nitride, in between 2 graphene monolayers, their electrical conductivity goes back to being what it was for graphene monolayers. That process makes the tether much heavier now because you have a whole bunch of insulating material between the layers. There are technical issues that we are looking at for every one of the methods of powering. And in our current study report, we leave it as an exercise for the reader to look at the different options and decide for themselves which they think is the most practical. I clearly have a bias. I think the lasers from the ground is the way to go. Others don't agree with me. I don't know how to support the receivers for the microwaves because they're absolutely enormous. And sunlight is so diffuse that the solar collector that gathers enough power for a 20-ton climber is 63 meters in radius. So it also is enormous. There is an interesting option to get climbers out of the atmosphere, but it's not sufficient to get them the whole way. It's called reel out. If you have a reel at the surface of the Earth, you can simply unspool tether material and it will go up because it's under tension. And if you have a climber attached to it, it will go up. And you can do that up to 100 kilometers is easy for the space elevator. So you could fire up the lasers or other power beaming sources when the climber is out of the atmosphere. And it turns out that wind is a big deal. I've been doing some studies of wind drag on the PV arrays, and those are in the new study as well. It's really a big deal. So it may have to be the case that we stow any receivers in the atmosphere because drag just looks like a real problem. But first, let's look at the energy requirements. How much energy is required to put a kilogram in geo? Now, this calculation of delta E, the potential energy change, is actually a number that is higher than the next number that you're looking at, the 48.5 megajoules per kilogram. The number for a planet of the size of the Earth, which is not rotating, is actually in the 50s of megajoules. The fact that the Earth is rotating means the Earth helps fling stuff away from it. So the energy required to get up to geo is reduced to 48.5 megajoules per kilogram. And this is the minimum energy, not including any inefficiencies of transmission or electronics or anything like that. So if you have a climber that weighs 20,000 kilograms, 20-ton climber, it requires almost a terajoule of power of energy to get to geo. And you have to put all that energy in. And if the trip takes 8 days, which it does if the climber is moving at 200 kilometers per hour, then the average power over the trip is 1.4 megawatts. But what you see is that if you look at the requirements, and I can't believe I took that graph out, there is a graph of the energy required as a function of altitude, it's very highly stacked up at the low altitudes. So the average 1.4 megawatts means very little because you need 20 megawatts of laser power near the surface of the ground and practically nothing the closer you get to geo. So need number two, but after tether is need number one, need number two, very large, big freaking lasers. And in the book that Edwards and Westling wrote, Edwards imagined that it would be free electron lasers to deliver up to 20 megawatts of power to the motors. Now, free electron lasers are capable of delivering multi-megawatt beams, and we've looked at what are the limits of what a free electron laser can deliver. But it's currently 360 times more power than any existing free electron laser in history. And the military has tried to build these things. They put a lot of effort into it 20 years ago and abandoned it. They abandoned the laser program, even though compact free electron lasers were designed that could theoretically fit on a 747. There are significant differences between what the military was looking for in their laser and what we need as a power beaming. The military was obviously not looking for power beaming. It was looking for using the beam to destroy missiles. This is a modern design of a 5 megawatt free electron laser that George Neal, who was one of the builders of the free electron laser at Jefferson Lab in Virginia, and I worked out together. The straight sections for this free electron laser are 60 meters long. They have to be 60 meters long because you need a lot of wigglers to wiggle the electron beam to produce the laser light that comes out. I'm not sure if everybody's familiar with the idea of a free electron laser, but it's basically an electron storage ring. It's a particle accelerator where the electrons are wiggled by very high magnetic fields over very short spaces. So when you take an electron and you shake it, basically synchrotron light comes out. And if you shake it the way a wiggler shakes it, you can get laser light out. So this is a very oblique view. I took a section view of the CAD model shown here along that line, along the wigglers out to the end where there's a window that the laser gets out. And the beam has to be allowed to expand. It has to diverge coming out of the wigglers for 61.5 meters. Because if it doesn't diverge to this diameter when it passes through the sapphire window at the end of that beam pipe, it will destroy the window. So there is there's a definite limit to the smallest beam size that contains 5 megawatts of power to prevent it from destroying mirrors and windows and other optical elements. And this is what a concept design of what the free electron laser would look like in relation to a moderate sized, this is not a nuclear aircraft carrier. This is a model I found of a non-nuclear carrier, and it's smaller than a Nimitz class carrier, but it would be very, very convenient to have a nuclear reactor on board to drive all the power systems associated with the FEL. This is the beam expander, and there's where you get a big difference between what the military is looking for and what the space elevator is looking for. It turns out that laser light diverges as it goes through a vacuum. Even if it is a high quality diffraction limited beam, the farther the beam goes out in space, the wider the beam gets. And it turns out that if you start the beam with a very small waist, it blows up faster than if you start it with a large waist. And a 2.5 meter diameter waist, which is the narrowest part of the beam, is a reasonable beam diameter to start, such that it doesn't grow too quickly and waste the power by missing the climber altogether. That's the issue. If the beam diverges too fast, the climber's receivers are only so big and will only receive a fraction of the power being delivered. So it's convenient that you need less power the higher you go, because the climbers that are up at high altitudes are going to miss some of the laser power. The laser is going to diverge. It's a matter of matching the laser power to the receiver size. And this is the beam expander that I designed that takes the beam coming from the free electron laser and runs it through a offset Cassegrain telescope to expand the beam up to a 2.5 meter diameter, 2.5 meter radius, waist, 5 meter diameter beam. And this is the idea. If you launch a climber every day and it takes a week to get to geosynchronous orbit, then there is an array of roughly 8 climbers spaced, because they can only climb 4,800 kilometers in 24 hours if they're going 200 kilometers an hour. So each one of these climbers has its own array of lasers powering it. And you can see that the total FEL power declines substantially as you go. The power required for the lowest climber is on the order of 11 megawatts, and it goes down to 41 kilowatts when you're up at climber 8, which is very close to geosynchronous orbit. You can also, knowing how much the free electron laser power is and how much shaft power you're getting at the climber, you can calculate the system efficiency. And you can also calculate the wall plug power that you need. So we need 14 lasers, 4 of them for the first climber that are operating at a full-blown 5 megawatts for the first day of climb. And then after that, the lasers are tuned down in power to be only what the climber needs to climb at 200 kilometers an hour. If you provide the climber too much power, it will either try to ascend faster than it's capable, or it will just overheat. So there's no reason to send it more power than it needs to climb. So this is the transfer function that I came up with that looks at here's the wall plug power in at the ground, the laser efficiency, the atmospheric transmittance, the laser power received. The atmosphere actually absorbs about 30% of the power just in going from sea level to outside the atmosphere. That's a bit annoying. I wish there was some way to avoid that, but there isn't really. The air is going to absorb some power. There's the photovoltaic efficiency. I put this number at 40% conservatively. It's possible, if enough research is done on VEHSA photovoltaics in the 500 nanometer range, which is the green light that we want to use, that the efficiency could be as high as 70%. But no one has done the work. They've done the work to get efficiencies on that order for near infrared light in the 800 nanometer range. That wavelength is too long for us. It diverges too quickly. Then there's the drive electronics efficiency and the motor efficiency, which I gave as an average of 80%. And actually, I changed that average to 96% when the motor does get to its full speed. It's 80% starting out in the atmosphere when it's or at 100 kilometers rather, when it's not moving at full speed, but it's moving at full torque. And then the efficiency, we have motors that are at that kind of efficiency. But you can see that the system efficiency is less than 10% for every altitude. And it turns out, even though a microwave transmitting system can have higher efficiency than an optical transmitting system, the wavelength is so long that it diverges so quickly, the receivers have to be too large. So the system efficiency is not what determines feasibility for the power beaming system. It's the weight of the receivers on the climber, and the optical receivers are the lowest mass for laser light that you can get. The solar mass is way larger than the laser receiver mass, just because, well, read the report. You'll see the details. This is cover art from our upcoming study report, which shows a climber receiving laser light from 4 5 megawatt FELs mounted to 2 aircraft carriers. Now, of course, you wouldn't put the aircraft carriers that close to the base. And the base is actually going to have many more facilities on it. It needs repair shops, it needs warehouses, it needs facilities for people, the base is going to be very large and similar to a very large scale oil platform. But the idea is the same. If you're starting out the climber at 100 kilometers up, I couldn't show everything on the same picture. So this is showing it at about 50 or 60 meters up. I forget exactly how far up it is. But you back the aircraft carriers away from the tether to power the climber higher up. And the higher the climber gets, the closer the beams get to being pointed straight up. The angle becomes very small when the climber is at tens of thousands of kilometers up. So this is the current concept model of a 20-ton climber. These gray tanks that are here and here represent 5 tons of liquid oxygen each. And these are 5-meter diameter PV arrays held out on cantilevered arms. And there's all kinds of engineering that still has to go into this. I'll talk a little bit later about this blue shell. This blue shell is just a placeholder for a thermal radiator to dump the waste heat off the climber. But getting back to what the Earth anchor would look like, here is a real thing that was built called Sea Launch. And we're looking at an Earth anchor that would be very similar to Sea Launch. Now, this one has the lasers mounted on the platform. That's not necessary. It would be fine if they were some distance away. It also prevents shadowing problems. If you've got 8 climbers on the tether at the same time, you can't mount all of the lasers near the base of the tether. They have to be staggered further away so that they have an angle to reach the climber without hitting the one below. I was the first person to identify the problem of PV shading by other climbers, and it's geometrically it makes putting climbers close together on the tether very, very problematic. So another Earth port design issue that is a big deal, and I have tried to get an answer to this. If you're going to miss satellites and junk in low Earth orbit, the idea is you move the base around, you move it back and forth, the tether shifts and misses the object that passes through its trajectory. We need very accurate knowledge of the position of the satellites, the junk, and the tether to move the base as little as necessary. And right now, we have not been able to pin down if that motion is plus and minus 100 meters or plus and minus multiple kilometers. And it makes a huge difference as to what the platform looks like that the lasers are on and how you move them around. I also think that we can use the lasers to ablate some of the junk in orbit and make low Earth orbit much cleaner. It needs to be cleaned up. It's seriously problematic. The Edwards book, written over 20 years ago, talks about a lifetime of so many days between objects that could strike the tether. Now that lifetime is on the order of 10 minutes because of the amount of things that have been launched and the amount of things that we know are up there that we track every day. It's a big deal. So the ISEC vision is to have at least 6 two-space elevators at each location, evenly spaced around the globe. And for 20 some years, we assumed that all of the traffic would be upwards bound. And very little work has been done on the descending problem. And the descending problem turns out to be very difficult because for the same reason that you can't put a battery on the climber and drive it up, you can't put a battery on the climber and let it go down and use regenerative braking to control its speed and put all that power in a battery. We just don't have the technology to store that much energy in a space that fits on the climber. So there are really only 2 things we can do. We have to figure out a way to beam that power off the climber. And the only practical scheme that we have right now are graphene resistors that take the electrical power from the motors on the climber and run them through a resistor and convert it into heat and just radiate the heat away. So the resistors would be glowing at a white hot glow as you get down, especially into the atmosphere where the energies that you're releasing are equivalent to the energies that the climber needed to climb. So we're talking resistors that are dumping megawatts of heat. That's all covered in the study report. It'll be coming out. 20 years ago, I started working on the construction climbers and was never able to satisfy the mass budget laid out in Edwards and Westlings' book, because when you start putting real components in and trying to figure how hard you have to squeeze the tether material, one of the problems of the graphene material for the tether is it's very slick. We use graphene, we use graphite as a lubricant, a solid lubricant on Earth. Now, in the atmosphere, it's likely to also be slick. Once it's out in space and the water evaporates off of it, the coefficient of friction is likely to go up. So it'll be easier to climb in a vacuum than it is on Earth. The graphite is not used as a lubricant on spacecraft because it stops working when it's exposed to vacuum. With more little trivia facts that we discovered relatively recently. So need number 3, lighter and stronger motors. I did the conceptual design using these motors from a company called Magnix back in 2022, who was offering an aircraft grade motor to electrify regional aircraft. And it was about slightly over a 0.5 megawatt motor. And what I discovered in going through the design process is, given its maximum torque, it did not have enough torque to lift the climber. I ended up with a 20-ton climber that had no room for payload and couldn't even lift itself. So in 2022, when we wrote the study for the climber tether interface, I simply had to imagine a motor that was at least twice as powerful as the Magni motors that were proposed back then. These motors are becoming available on the market now. Electrifying regional aircraft is still the best place to look for very light motors with high torque and high power. They are liquid cooled. The next hurdle that has to be crossed is they have to be designed to operate in vacuum. So that's the next challenge. So I mentioned that I looked at the design of arms to support 5-ton loads. The 20-ton climber that I ended up with had the capability to support 10 tons of payload. So I said, okay, if we're going to do a LOX and fuel depot up in GEO, what does a 5-ton container of LOX look like, and how do I attach it to the climber? And I started drawing these arms made out of carbon fiber reinforced polymer. And it turned out that 5 tons is a lot of weight. You need a lot of structural material to hold up 5 tons. And this is what it ended up looking like. I had to put shear panels, and I had to double the number of arms. And I have not come up with a connection scheme between the tank and the arms, which is convenient to use at GEO when you want to let them go. At GEO, you would probably need a space tug to take them off the climber and put them in the depot. These are all elements of infrastructure that still need to be worked out. The waste heat problem. Back in 2022 up to 2024, we knew that the motors could be made 96% efficient, but that meant if we were dumping 4 megawatts of power, which is roughly what the motors and would dump if they were 96% efficient and operating at 4 megawatts, it's 160 kilowatts. So I calculated the amount of area of a space radiator that's necessary to dissipate that much heat in space by thermal radiation if it can only heat up to 200 degrees C. Now, this completely ignores the amount of heat, waste heat, that happens to the photovoltaic arrays. We need to keep those between 80 and 100 degrees C, and they're only 40% efficient, so they're heating up tremendously. And we have not worked out the full thermal balance of a climber. It's a big deal. And you also have to avoid absorbing energy from direct sunlight. So you need special paint that has a high reflectivity for sunlight. Turns out radiating waste heat away in space is a big deal unless you can get the temperature of the radiator up very high. And the only way to do that, since the components that you're cooling are limited to about 200 degrees C, is to put a refrigeration system in. And I have not had the time to design and size a refrigeration system that would allow me to run the thermal radiator hotter and still keep the components that are being cooled at 200 degrees C or less. So that's yet another thing that has to be worked out. And I also started looking, I started looking at the climber as a machine that you have to assemble onto the tether at the earth port. So I started viewing it as two separate machines that you couple together. So I came up with devices that I call quick disconnect mechanisms that interface. You need 40 tons of load coming from these green jacks pressing the wheels against the tether so that you get enough traction. That 40 tons of load has to be reacted by the structure of the climber on both sides in tension. And if something happens to the climber at some altitude, you want to be able to eject it off the tether so that you're not tying up an entire tether. So that means the quick disconnect mechanisms have to be remotely operated. So there's motors and gearboxes and drives associated with those. I then looked at, now I've got a 20-ton climber that can lift itself and it can lift 10 tons of payload. What if I want to lift 200 tons of payload? And I said, well, the elevator basically scales linearly. So I just stacked up 10 20-ton climbers to get a 200-ton climber. What I should have done in this picture is left the PV arrays turned on, the 5-meter PV arrays, because that makes it obvious that even if you rotate them, some are going to shadow others. And it becomes a logistics throughput problem for the elevator. How far apart can 20-ton climbers be that are close enough together so that you can up the amount of load, the amount of payload that the elevator is carrying, but they're not necessarily going to be connected together like this, because it's really not obvious how you power such a thing. And if it requires 14 free electron lasers to power 8 climbers that weigh 20 tons, it would take 140 free electron lasers to power 10 times as much weight. Haven't even begun to look at the logistics of what that power beaming scheme looks like. But this is what a 200-ton climber looks like compared to a 747. We build larger machines like this every day. It's not that big of a machine. It differs from a 747 in the fact that jets don't carry oxidizer, they only carry fuel, and they use the atmosphere for the oxidizer. That's a huge weight savings. And they don't go straight up, which is what climbers on the elevator have to do. So working out those very large scale climbers is definitely a work in progress. I know that I can design a climber that can carry that can weigh 60 tons and carry 30 tons of payload. It's not obvious to me how to get up to multi-100-ton payloads. It's also not obvious to me how to go in the other direction, because as I tried to design smaller climbers, the structure seems to have a minimum threshold of mass, which means you can't say I'm going to design a bazillion ant-shaped or ant-sized climbers. So there is a design space that we are currently working out. These are just a list of some of the challenges associated with the space elevator. LEO objects is a big one. Micrometeors is another one. Induced electric currents doesn't seem to be a big problem because the elevator doesn't actually move that fast with respect to Earth's magnetic field. The magnetic field occupies a certain shape as the Earth orbits around the sun. So as the Earth rotates, the elevator does change its relationship to the field lines. So there is a certain amount of current generated in a conducting tether, but it turns out to be milliwatts of power, and the elevator will absolutely just dissipate that. There are induced oscillations that the moon and the sun have gravitational connections which don't couple very well with the natural frequency of the elevator, so we don't expect there to be a resonance. Radiation is kind of a big deal, but it's also possible that the elevator could be used to discharge the Van Allen radiation belts. That's kind of a concept we've been thinking about, which would reduce the radiation problem. It would never go away because Van Allen radiation belts are constantly being recharged by the solar wind, but it could potentially be reduced. The mid-level of the atmosphere where there's atomic oxygen, that stuff is highly corrosive. And there are a couple of proposals for what you do with the tether in that region, like coating it with nickel or something like that. Of course, anything like that makes the tether heavier in that region, so you have to work it out from the point of view of the dynamics or of the masses of the tether material. Lightning is a big deal, and you mitigate that. So you're already on the equator. The winds on the equator all around the world are at their minimum speeds. And if you are, for example, the first tether base we're talking about is off the coast of Ecuador, some hundreds of kilometers west of the Galapagos Islands. And that area of the ocean has the lowest wind speeds and the least probability of lightning strikes. So there are all kinds of things that we have to work out. Personally, I think that the constellations of satellites that people are putting up are a bigger problem. 60,000 satellites in low Earth orbit for the Starlink system, and other companies are putting up their own constellations. Eventually, the sky becomes very crowded. And then you ask the question, is it reasonable to wiggle the tether to avoid all of these satellites? And I don't think we know the answer to that just yet. We need to do another. We've done debris studies and satellite avoidance studies, but the numbers keep changing, and LEO keeps getting more and more crowded. They used to make the argument that space is big. Well, NASA has concluded LEO is actually not that big. MEO is still big and GEO is still big, where collisions are few and far between, but LEO is crowded. So, in conclusion, the space elevator can substantially reduce costs. It can act as a transportation infrastructure that funnels material off Earth and funnels other material, asteroid mined materials back to Earth. And from my perspective, whoever builds the first one owns space, because you have the easiest way to get into space. We just need a tether material that's about 200 times stronger than steel. We need lasers that are 300 times stronger than the power of existing lasers. We need high performance motors. And all of these things have terrestrial uses. You can make money on Earth by developing any of these things. And that is all I have. I welcome questions. I hope it was comprehensible.
Sorry, Larry, I was trying to be clever and use the space bar to unmute myself, and it didn't work. Thank you for a very interesting talk. Lots of details. I'm sure that people have picked up different things. We do have this problem with this this fire alarm that's causing a bit of a feedback problem. So I will be turning on and off the audio. It is questions and answers.
I don't hear the fire alarm. The Zoom has pretty good noise cancellation, and I'm not hearing any of it.
We are getting some feedback from somewhere. I'm not too sure where it's coming from. So, as usual, ladies and gentlemen, if you've got a question online, will you put up a digital hand? In the room, can you attract my attention in some way? While people are just thinking about it, Larry, if you've got this tether, and I'm going to ask you a question about the tether itself in a bit, but if you've got a tether and you're moving it around, you're wiggling it around at one end, try and keep things out of the way of it, isn't there an issue about setting up some sort of wave up and down the tether?
It absolutely does set up a wave. And the tether material, even though it's the strongest material in the world, the spring constant of the tether is actually quite low. One of the things we don't know at the moment is what is the damping ratio for this material. But it looks like a very soft spring. And my guess is with a tether that's made up of tens of thousands of layers, the damping ratio is probably going to be relatively high. So those vibrations are going to be damped out and turned into heat. I don't expect them to reinforce and cause a resonance problem.
Okay, thank you for that. And in the room, Graham, please, your question.
Is it projected to have a very considerable taper in this tether? Obviously, the stress in it isn't going to be the same throughout the length. So are you going to taper it, or is it not practical to have a taper?
It is the optimal, the lightest tether you can build is a tapered tether. You don't have to build a tapered tether, but then you're making a heavier tether that costs more and is more difficult to put up. So yes, it's tapered. The maximum cross-section of material is at geo. It tapers towards the 100,000 kilometer apex, and it tapers towards the Earth.
That's two questions answered at the same time. Thank you.
You can either taper in width, or you can taper in thickness, or a combination. Actually, we haven't learned how to splice this material, so we don't have a good answer to that one yet either.
Can I just ask a follow-up question to Graham's then? Before this talk, I envisaged this this cable to be like a tapered suspension bridge cable, which would be circular. But your diagram suggested a ribbon.
Yes.
Now, how are you going to form that ribbon by dangling threads of it from above?
Oh, no, you don't dangle threads. It's always a ribbon. It's spooled up on a spool as a ribbon.
I don't see how you're going to sort of combine the different spools into one ribbon, whether it's tapered or not.
So that is a challenge. The original deployment scenario that had multiple ribbons being attached together sounded like a really good idea at the time, and it's not clear that it actually works.
Okay, I'm looking for other questions in the room. Roy Hudson.
Yeah, Larry, you talked about the cable passing through the Earth's magnetic field, and the current generation was going to be low. But what about effects like coronal mass ejections? The sun's effects on basically a large aerial conductor poking up out of the atmosphere.
That's a good question. I don't expect the coronal mass ejection to cause, I suppose it is a charged plasma passing through the Earth's magnetic field, so it could generate a voltage on the tether. But again, we learned that this multi-layer material has its electrical resistivity is actually very high when it's multi-layer. So if a voltage is set up across it, the current will be dissipated by the resistance.
Okay, Henry, online, can we have your question, please?
Why do you envisage it being the tether being on the ocean rather than on land? Would that make life a lot easier?
It's a good question, Henry. And it was originally thought about in the ocean for the reason of moving the platform around as a floating platform that could move as needed.
Right, let's see if that's just solve that feedback problem. Can we have your answer again, please, Larry?
I'm sorry, can you remind me of what the question was again?
The question was why put the base of the tether on the ocean rather than on land?
So the original reason was it looked like it was going to be necessary to move the base around to avoid objects in LEO. And that seemed to be easier in a floating platform than on land. You could certainly do it either way. You just have to figure out how much land you need, what kind of tracks you're going to put everything on. It's challenging. I've actually looked at a platform that has tracks on it. If we don't have to move the tether by more than plus and minus 100 meters, things become a lot easier. The platform itself doesn't have to move, and that makes it easier to do on land. You can design a platform that has tracks on it that is 200 meters in diameter and moves the base of the tether back and forth by 200 meters. If the motion is on the order of kilometers, it's much harder to talk about a single structure holding the base of the tether that can move that far on land. I mean, sure, you make a giant train platform. I've never seen anybody even think about what that would look like on land.
Okay, Peter Lloyd, online.
Yeah, thank you. I've been thinking about this idea of causing a wave to travel up the tether in order to avoid junk moving around and so on. I can see that if you wobble the bottom, you'll get this wave going up a tether, but doesn't it make a big difference if you've got heavy weights distributed up the tether?
Absolutely. The wave will reflect off the climber. Yes. And there may be a need for the climber to have some kind of cold thruster that helps move the tether. It would be a consumable, and it would add mass to the climber. That takes anything you add to the climber takes away from payload. But you're absolutely right. Waves on the tether reflect back off the climbers.
Yeah, good. That's what I thought. And actually, if you were able to have some sort of reactive thing on the climber itself, you could as well watch an object coming in and just move it out of the way just in time.
The objects that are coming in at 17,000 miles per hour.
That's a bit fast.
and some of them are flecks of paint and bolts and things like that. So could you do some of that debris avoidance? Maybe. And I think that would be an excellent idea. But yeah, things that are in orbit are going very fast, and they're potentially extremely damaging.
So you've got to know well in advance, because if you're going to do it by moving the base of the damn thing, and the wave has got to travel up this long length past all these reflective masses on the way up, by the time you get halfway up, it's not going to move.
And we're trying to develop a simulator, a space elevator simulator that would allow you to simulate those dynamics. It turns out to be a bear.
I suspected so. Thank you.
Okay, we've got a question from John Dunthorne from Cleethorpes AS on chat. Would it be more practical to build a space elevator on the moon, 16G, etc., if we could find the stuff we want to mine.
Okay, now here's the thing about the lunar elevator. It is easier to build an elevator on the moon because of exactly that reason. And you don't need, we have materials that are strong enough today. The problem with the moon is it's not spinning fast enough. The moon's geo is, it rotates twice a month. So it's rotating too slow. So the kind of elevator that you build on the moon is actually dynamically stabilized. You would drop a line from the near side of the moon towards the Earth, and the gravity gradients between Earth and moon would stabilize it. As actually it would pass through a Lagrange point. So it is an elevator that is a completely different animal. And eventually we'll have those, but the reason that we are focusing so much on designing an Earth elevator is because that's where we are. There are people who are looking at lunar elevators and they're looking at Mars elevators because we already have the material to build such an elevator, but there's no one living in either of those places. We have to be able to get off this world.
Okay, John. Would
Okay, thanks.
you like to follow up?
Yeah, it's interesting. I did wonder whether the moon's rate of rotation was part of the problem. So that's interesting. Thank you.
Okay, thank you, John. I'm looking around for any other questions. Tony Morris in the room when the microphone gets to him.
Hi, Larry. On your laser wiggler diagram, I don't know whether I misheard, but you said the sapphire window is 2.5 meters in diameter.
No.
The
The window is much shorter than that, much smaller in diameter than that. The beam only has to expand at the window to about 20 centimeters to have a low enough power density to make it through the window.
Okay.
I forget if this is a 12-inch beam pipe. I forget what size beam pipe and vacuum flanges I chose for that one. But it's not that big. Most of the expansion happens later in the beam expander.
Yeah, in the Cassegrain beam expander.
Yeah.
Yeah, okay. That's fine.
When you get a sapphire 20 centimeters,
Well, not so much. We've never made a lens at 2.5 meters, so I thought I misheard.
no, finding a sapphire that's 20 centimeters wide. Oh, fair enough. Oh, all right. Okay, one of our members just saying that sapphires are quite easy to manufacture to large sizes. So
Yeah.
we'll Graham, I doubt your greater knowledge. Okay.
With a 5 megawatt beam passing through that window, there's enough absorption that even though sapphire is a very good optical transmitter, some power is going to be absorbed by the sapphire. Most FELs have cryogenically cooled sapphire windows.
Okay.
I don't show any of that.
I think we'll make this the last question. Henry, can we have your question, please?
Yeah. We hear complaints by astronomers about the Starlink satellites. Would your laser beams cause problems for astronomers?
So there is reflected light off the PV arrays, and we've done some calculations. The main issue that makes us think it's not a problem is the fact that the elevator is located relatively far away from land, from astronomical observatories. Even if you're at an observatory in Chile, you're a long ways away from where an elevator would be. And you also know exactly where the elevator is, and it doesn't change that fast, or it doesn't change direction. Whereas there are Starlink satellites everywhere all the time.
Would it affect the night sky for the people on the ground?
No, I don't think so. What some people are worried about is that the frequency and the power might be enough to blind Earth's satellites that are looking down at the Earth, and that could be problematic. And that's one of the many political issues that have to be worked out.
Thank you.
Okay. Ladies and gentlemen, will you please join with me in giving Larry a big Max Bryn Swinton astronomical thank you. Thank you very much, Larry.
Thank you.